Okay. So the next talk is by Mohammad Roghani, who will tell us about approximate matching and how it requires almost quadratic time.
Thanks for inviting me. I'm very excited to present our recent results. This is a joint work with Sohail, who is also here, and my advisor, Aviat. I'm going to talk about approximating maximum matching requires almost quadratic time. So first, I'm going to define the problem. Matching is a set of edges without shared endpoints. And maximum matching is the matching with maximum number of the edges. Here in this graph, the set of red edges is the maximum matching of the graph. And our goal in this problem is to estimate the size of the maximum matching in sublinear time with respect to the number of the edges. So here, we want to spend subquadratic time. So we're interested to maximize the approximation ratio and also the running time to be smaller than n squared. So in this talk, I'm going to use n as the number of the vertices and delta as the maximum degree of the graph. So there are two regimes that people think about this problem. So one is the sparse graph regime that delta is bounded. For example, delta can be constant, or more generally, it can be n to a small of 1. And the focus in this regime is to design algorithm with dependency only on delta and not on n. The other regime is dense graph regime that the delta is not bounded. It can be as large as n. And the focus here is to design an algorithm that estimates the size of the maximum matching in n to 2 minus some omega of 1. Because we're not allowed to see the whole graph, it's important to fix the access model to the graph. So there are two models. One of them is adjacency list, and the other one is adjacency matrix. In the adjacency list, we can query the ith neighbor of vertex v. And in the adjacency matrix model, we can ask if there exists an edge between vertices u and v. So the trivial approach here is to query everything in the adjacency matrix or the adjacency list. It needs n squared queries. And as also Sepper mentioned, that if you want to find the edges of the maximum matching, this is the best you can do. You need n squared time to find any constant approximation for maximum matching. So here our goal is to just estimate the size of the maximum matching. And in this talk, I'm only considering the adjacency list model. Any question about the model and the problem? So there are people have started to think about this problem for the sparse graph regime more than a decade ago. There are many results on the sparse graph regime that started with the work of Parnas and Ran. I'm not going to discuss about the results in the sparse graph regime, and we'll jump to the dense graph. So for the dense graphs, all the results can be summarized as these three results. So the first one is that Sohail proved that you can get half approximation in linear time with respect to the number of the vertices. In another paper with Sohail, Aviad, and Amin, we proved that you can get a slightly better than half approximation if you spend a slightly superlinear time. And Shayan, Peter, and Tachapol proved that you can get 1 minus epsilon approximation in a slightly subquadratic time. So here is the trade-off between the time and approximation ratio of existing algorithm. So there are two algorithms that gets roughly half approximation in near linear time with respect to n, and also the result of Shayan, Peter, and Tachapol that gets 1 minus epsilon approximation in a slightly subquadratic time. In terms of lower bound, Parnas and Ran proved that if you want to get any constant approximation, you need to spend omega of n time. So if we put this lower bound in the plot, so we know that there exists no point below in this orange area. So up until very recently, this was the best lower bound that was known. So in this talk, I'm going to show how you can make this lower bound all the way up to here. So basically, the question is that can we get 1 minus epsilon approximation in linear time? So this was open until 2 years ago. So we proved that any algorithm that gets better than 2-thirds approximation requires to spend n to 1.2 time. In another paper, also, we proved that if you want to get 1 minus epsilon approximate estimate of the maximum matching, the algorithm needs to spend n root n time. The focus of the second paper is mostly about the sparse graph regime. Yeah, if you want to know more about it, I'll have a poster in the Vola about it. So if we put these two new lower bounds in this plot, so we have this neutral plot that you cannot have any point in this purple area and also this blue area. So it's still this question that if you can get 1 minus epsilon approximation that runs in, like, say, n to 1.999, that doesn't depend on the epsilon. The advantage over n squared doesn't depend on the epsilon is open. So we answered this question negatively. We proved that if you want to get 1 minus epsilon approximation for estimation for the maximum matching, the algorithm requires to spend n to 2 minus some function of epsilon. So basically, this result shows that the algorithm of the Cheyenne-Peter and Tachapol is optimal if we ignore the dependency on the epsilon. This result also holds even when the graph is bipartite, and also when we are promised that the input graph is either have a perfect matching or matching that leaves at most epsilon n vertices unmatched. So this new result shows that this algorithm here is optimal. So I'm going to talk about the previous ideas for proving lower bound. The general framework is that we have two instances. One of them is, I call it yes case. In the yes case, the graph has a perfect matching. And in our no case, the graph this maximum matching of the graph is far from being perfect. And we want to somehow hide some of the maximum matching edges. So we want to show that a constant fraction of the maximum matching edges are indistinguishable. So I'm going to call these two yes case and no case as the core graph, because I'm going to add some more vertices in the next few slides. So the first idea that I call it idea 0, because it gets back to the work of Parnas and Ran. It's the dummy vertices idea. So we can add epsilon n vertices that are connected to the whole graph. So if you have some core graph, we can add epsilon n vertices and connect it to everyone. And then these dummy vertices doesn't change the size of the maximum matching that much, but only by additive of epsilon n. But they will increase the cost of the adjacency least squares a lot. So for example, if the degree of the core graph is d, then we expect to spend n over d queries just to see one edge inside the core construction. So we spend a lot. So for example, if d is constant, after n queries, we will only see one edge inside the core graph. And that's why the intuition behind this diverse is to just increase the cost of the adjacency least squares. So basically, the work of the Parnas and Ran uses dummy vertices idea to prove that any constant approximation requires omega of n queries. So in our yes case, we can have a perfect matching in the core graph. And in the no case, we can have an empty graph. So if we spend less than n queries, all the queries are going to the dummy vertices, and we don't have any queries inside the core graph. So we cannot distinguish between the yes case and no case. So any constant approximation requires to spend an omega of n time. So this next idea is to we call it camouflage the maximum matching edges. So when we have superlinear algorithms, this algorithm is going to see some of the maximum matching edges, and we need to somehow hide those maximum matching edges and to prove and show that those are not distinguishable for the algorithm. So they should be locally indistinguishable comparing to the other edges. Also, because we are proving hardness of approximation, the yes case and no case should be far from each other. So the max matching edges globally look different, but a constant fraction of them should be locally similar to other edges. So for example, here in this construction, if you look at the edges of the maximum matching in the middle of this gadget, they are locally similar to other edges. So you have to go all the way to these vertices that we call S to just see the difference between those edges and the other edges. The next idea is the reduction to forest. So we want to show that all those previous lower bounds prove that they will see only a forest inside their core construction. So if we set d small enough, d is the maximum degree in the core construction, the algorithm will never see a cycle in the core construction. I can show you an example why this is true and where this n to 1.2 lower bound appears. So suppose that the degree inside the core construction is n to 0.2, and the number of the queries is n to 1.2. And assume that all the graph inside the core construction is somehow random. So each query that the algorithm makes has no dummy endpoint with probability d over n. So if the algorithm makes q queries, the number of the edges that the algorithms will see inside the core construction is bounded by n to 0.4 minus a small of 1. So the number of the pairs of vertices that have a degree larger than or equal 1 is bounded by n to 0.8. And also, because we assume that the graph in the core is somehow random, the probability of having an edge between those pairs is bounded by d over n. And if we multiply these two numbers, we get the expected value of much smaller than 1. So we expect to see no cycles inside the core construction. And why this property is important for proving lower bound? Because we want to show that some of the maximum matching edges are indistinguishable, and we use different techniques such as correlation, decay, and coupling that are much easier on the trees comparing to the graphs that have cycles. So I'm going to wrap up the previous ideas. So we add dummy vertices to increase the cost of the adjacency list queries. We also set the max degree of the core construction small enough to prove that the algorithm only sees a cycle inside the core construction. And also, we hide some of the maximum matching edges. And some more ideas like correlation, decay, and coupling to show that these subgraphs are going to be similar in our yes case and no case. These techniques used to prove that if we want to get better than two-thirds approximation, we need to spend n to 1.2 time. And also, if we want to get 1 minus epsilon approximation, we need to spend n root n times. In the next few slides, I'm going to talk about this n root n threshold, the barrier that we have to pass through. So we call it cycle discovery barrier. So even if the degree of the core construction is constant, it's still 1 over n fraction of the edges have no dummy endpoint. So for example, if we have n root n queries, we expect to see n queries inside the core construction. And using a Bhattacharya paradox argument, we can prove that the algorithm will eventually see some cycles inside the core construction. And the reason is that the algorithm can start to run a BFS from some vertex u, and also from another vertex v. After seeing root n vertices, these subgraphs are going to collide. So they have some intersection. So then we will see some cycles. Also, this looked like the limitation of the techniques that we use to prove the lower bounds, but there exists an n root n algorithm that solves our instance for FOCS 23 paper. So also, this cycle discovery threshold is the true bound for some other problems. For example, Goldfish and Run proved that root n time is needed for bipartite testing, also on the assumption that the faster algorithm cannot see any cycles. Later, they proved that there exists an algorithm with root n running time for bipartite testing. So we use a recursion on the construction that we previously have to make the lower bound stronger. We start with our base construction. We call it G0. This is exactly the same construction that we used for the previous lower bound. And we construct L from GL minus 1 in a way that instead of having matching edges here, we embed one graph from the one level below. So when we want to construct G1, we use G0 as we embed G0 in these gadgets instead of the matching. And this recursion happens for a large number of for large constant. And all these buckets are just irregular graphs, irregular graphs. And this the degree of these the construction gets larger and larger as we go up to the hierarchy. And the only difference between our yes case and no case is if you go to the very middle part of the construction as you go down, when you reach the base construction, these middle edges doesn't exist in the no instance.
So these lower instances, are they all yes instance or no instance?
Yeah. So in our base construction, the middle edges doesn't exist.
Yes.
So when we want to construct the next gadget, in the middle one we use GS or GNO, based on the fact that if it's going to be yes or no in the final construction.
The other ones are no.
Yeah, no, all of them are yes. Yes, it doesn't matter. So previously we tried to camouflage the maximum matching edges. Now we are camouflaging the subgraphs that we use inside the construction. So basically, we proved that in the highest level, the algorithm will see some cycles, will discover some of the edges that belong to the middle subgraph, but it loses this advantage as it goes down through this hierarchy. And when it reaches the base level of the construction, it doesn't see any cycles, and then we can use the previous known techniques to couple and use to show that the yes case and no case are indistinguishable. So I'm going to give an example why this will happen. So suppose that we want to, the algorithm can see root n edges of the graph. There are two types of ways that the algorithm can see root n edges. One is to run a BFS and see a component of size root n. In this way, we can use the same birthday paradox argument to show that the algorithm will see cycles. Now suppose that the algorithm only sees root n random edges of the graph. For this case, we can show that all the components that the algorithm see are small components, and the algorithm will never see a cycle if edges are chosen randomly. So what we prove is that if we start from the highest level, the algorithm can grow a large component, we'll see cycles, and we'll learn that some of the edges belong to the middle gadget. But as it goes down to the hierarchy, the algorithm, the case will be closer and closer to the scenario 2, and the edges will be random. So the algorithm cannot grow large component, so it cannot distinguish between the yes case and no case when it reaches to the base level of the construction. And then we use the previously known techniques to just couple the two instances. So yeah, that's the main technical part of our result, that we camouflage subgraph inside and the previous results was based on camouflaging the maximum matching edges. And we were able to show that 1 minus epsilon approximate estimate of maximum matching requires n2 2 minus f of epsilon. Again, this holds even when the graph is bipartite or is promised to have a perfect matching or a matching that leaves epsilon and vertices unmatched. I'm going to show this plot one more time, and we'll wrap up with open questions. So still, if you look at this plot, for 1 minus epsilon approximation, the problem is settled down. For half approximation also, the problem is settled down, but we don't know anything in between. So if we want to get two-third approximation, what's the best running time that we can get? Or, for example, we want to spend n root n time, what's the best approximation ratio that we can get? Or can we get, say, two-thirds in linear time? Yeah. Thank you. I'm happy to answer any question.
Like very loosely, what does the function f look like for both the upper and lower bound? Are they like crazy?
It's the dependency on epsilon is terrible. So for example, if you want to, it's doubly exponential, I guess, for our lower bound.
Okay. And what about the upper bound?
For the upper bound, so do you remember the?
Also exponential, but in the other way.
In the other way, yeah, I guess.
But
Okay.
yeah, both are exponential. Exponentially far apart.
Okay.
Yeah.
But they all go to zero as epsilon.
Sure, sure. Yeah.
So if you do your construction to say 4 levels and stuff, do you get move it from n to the 1.5 to n squared in some nice linear way? Or?
I think so. You can show that if you use fewer number of the levels, you can get some other lower bound, some weaker lower bounds. Yeah, with fewer queries. Yeah.
Like a technical question, in the instances you have, you can't find a partitioning along which edges belong to which instance, like which vertices belong to which instance. This shape, like, can the algorithm figure that out quickly?
The shape.
Yeah.
So the intuition for this instance is that if the algorithm wants to know if an edge belongs to this very middle part, it needs to find some path that goes to reach S. And this is not the final construction. We have some other delusive vertices to avoid some random walk algorithms. But yeah.
GL minus 1 there matters if you know it's always a no instance. So what is its task basically? Like on the very right side, for instance. It's always sampled from the same disturbance.
Yeah, from the.
So its task is to not allow it to explore from S to get to the middle.
So the layers, you don't know if you are in A2 or in A3 and have to spend time. So you add those, you embed those graphs all the way to the N2 just to make it hard to distinguish these layers.
So you don't know your graph.
You don't know this.
No, we don't know. And we use the same like subgraph for all these gadgets because there are some like you can come up with some silly algorithm that just see the degree of some vertex. So they should be symmetric and all of them should look similar.
So I didn't understand the answer to Venkat's question then. So you say that there is something that you can do with fewer layers, but so it's not giving you some additional lower bounds on this curve. So the missing, so when you go to the, if you flash the slide on the, yeah. So can't you then get something which is?
I think the dependence. Yeah, I think the dependency on, so the number of levels is doubly exponential with respect to the epsilon. So I think you will get something here, but I don't think it's going to be a.
It's not going to be the right
Yeah,
thing.
the right thing, yeah.
You can get some non-trivial lower bounds.
Yeah.
Any other questions? We have 15 minutes of discussion, so. I guess we could either, if there's no questions, we can start the break earlier, and the next talk then will be at 4.